Hello everyone. In this we're going to discuss what was called Dijkstra's algorithm. This is the algorithm we've been using as a shortest path algorithm. Dijkstra is a somewhat famous computer scientist and mathematician, and this is probably one of the most famous algorithms in computer science because of the ubiquity of shortest paths. So if you're going to pick an algorithm to kind of memorize and need for the rest of your life, this is definitely a good one to choose. So we have the simple implementation here in front of us. And if you notice, this algorithm is effectively identical to the point that you could almost do a find and replace from our minimum spanning tree algorithm to this algorithm and directly get them to work together. So we're going to find the shortest path from some node, v sub s, one of the arguments to the function here, v sub s, and we are going to do that by separating it into two parts. What we colored before with light purple, and then what we colored before with white. U here corresponds to all of the nodes not in the shortest path tree yet, and the g.v minus u is all of the nodes that we have colored already. So we're going to start by getting rid of vs and setting it to be the root of our shortest path tree. We're then going to keep running while there are nodes to add, and I can find an edge from the colored nodes to the not colored nodes. And then really the only place in this entire code that we have changed anything is in line 5 and line 6, which says we're going to choose v sub I and v sub j to be the edge from the colored part to the not colored part that has the minimum distance. This is our greedy decision. So it's the edge from g.v minus u, the colored part, to u, the not colored part, that minimizes the distance plus the weight of that edge. It's the least expensive to add currently. So we find that. V sub j is the edge that we are adding, and v sub I is the edge that already was in our spanning tree. So we are going to set the parent of v sub j to be v sub I, just like we did before by coloring with the deeper purple lines. We then update the distance to v sub j by taking the distance from to v sub I and then adding in the weight of the edge. We then get rid of v sub j out of the vertices that we need to add to the tree. It's the exact same as the algorithm we used for the minimum spanning tree, and therefore has the exact same runtime. So I'm going to leave it to you guys to try and follow the argument. If you want to, you can try to replicate it in its entirety, but the runtime is identical to the previous one. So it's going to be in theta of n times m. I'm not even going to write it down here. I'll leave it to you to go back to your notes and back to the video to add it in yourself. And hey, maybe we sit there and go, maybe we can make this better. Maybe we can store more information at the vertices. And you bet we can. So at each vertex, we're going to store the distance. And then we're only going to iterate over the vertices. The first one iterated over the edges, which turns out to be quite costly. This one we're doing exactly the same modification we did last time. In fact, when I made this code, I literally typed Control F, replaced cost with distance, and then needed to make other very, very minor changes. So this is almost identical to the prims algorithm we mentioned before. So we initialize the problem by setting all of the distances to be infinity, and then set the starting node to have a distance of 0, because it's next to itself. We then, while there are nodes to add, we are going to iterate and find the best of them. So now we are iterating over the nodes only. We no longer need to recheck the edges. The only time we recheck the edges is after we've added v sub j, just like we did with the minimum spanning tree. We are going to update the distances to every node that is adjacent to v sub j. Other than that, this is exactly 100% identical to prims. The only major difference is that we changed cost to distance, and instead of just having cost inside of this for loop with the edges, we now have distance plus weight. That is the only difference from prims to this algorithm. Doing that basic arithmetic of computing the distance plus the weight is not going to change the runtime, and therefore this has the exact same runtime as our modification to prims, which, if you remember, would be theta of n squared plus m. Therefore, this is the exact same runtime as prims, and I again encourage you to go back and look at the analysis we did there and perform that analysis on this version of Dijkstra's algorithm. And you can bet we're going to do exactly the same modification again. We can improve further by reducing that n squared term down to an n log n by using a data structure. What data structure? The exact same as we did last time. It's going to be a priority queue. So, our third implementation, we create a priority queue, here denoted as Q. We initialize it. We then insert every single node except v sub s into it. And then here it says v sub I should say v sub s. Let me update that quickly for us. This should say v sub s. I apologize for that. So we add every single node except v sub s to the queue, and then add v sub s with a cost of 0. And then while there are things in the queue, and we can find them, we are going to take out the minimum and add it to our spanning tree. So we compute the minimum distance, we extract the minimum, which had that minimum distance, and then we set up the parentage. Remember, when we were doing this, we had a parent and a shortest path parent, which again, you notice I didn't copy paste my code properly, because this should read shortest path parent, SP. So we update the shortest path parent. And then again, as you've clearly noticed, I blatantly copy-pasted this from myself and slightly modified the code. It's going to be exactly the same. The only difference is that instead of cost, we now have distance, which is computed as distance plus weight of edge. The only thing we had before was weight of edge. So before, we had simply weight v sub j v sub k. Now we have distance plus weight v sub j v sub k. So this is going to run in the exact same runtime as our modification of prims that used a priority queue. So the runtime of this would be theta of n log n plus theta of m log n. Exactly the same as prims. And again, I encourage you to try and replicate that analysis on this algorithm. I won't go through it. I trust that you can do it yourself. It is going to be identical to prims because all we have changed is our notion of our greedy choice. Rather than making a greedy choice by minimizing cost, we're minimizing distance instead. But other than that, this is exactly the same as prims, and therefore would have the exact same runtime. Conveniently, the coding here is usually simple for a greedy algorithm. The reason is that we are being as greedy as possible. It's what you might expect to do as your sort of first pass. Whether or not it actually solves the problem is usually the hard part with these. The coding is almost always easy as long as you know the idea. Or you assume, I'm going to make a greedy algorithm. This is a notion you should get into your head as a way to design an algorithm or a data structure is to decide, can I do this in a greedy way? There are two things you must do if you're designing a greedy algorithm. One, design the algorithm, typically the easy part. Depending on the problem, it might still be difficult, but it's definitely going to be easier than proving the correctness of the greedy algorithm. You need to prove that the local decision, the greedy decision of choosing the best path, will tend to be the best result. That is usually very difficult, and those proofs can be different for each algorithm you develop. But for this one, we'll have our shortest path theorems to verify the correctness of this algorithm. You could also verify this in a sort of standard computer science way by having preconditions, postconditions, and conditions that are true at every iteration of the loop. I don't quite remember what those are because I'm not a software engineer, but if you wanted to, you could use a more computer science approach and try and have that be verified. But then verifying those, you will again need a theorem or a proof. This is the primary reason that this class covers proofs, is because algorithms like greedy algorithms, it is not obvious whether or not they are true or whether or not they truly solve the problem you are trying to solve. So these algorithms are nearly identical to Prim's algorithms, and the only major difference is that our assessment of what is the best local decision to make. We saw that when we ran the algorithms, and the code is even more similar than running the algorithm itself. That's the last thing we have for shortest path algorithms, and I trust that you can, on your own, determine the runtimes and re-perform the analysis that we did today.